Hi guys, we're going to be looking at how to find the approximate area underneath a function. So basically, we're going to start with the basic function, and what we're trying to find is the area underneath this curve. Why do we want to find the area underneath this curve? Let's say this were a velocity versus time graph. In this case, finding the area underneath this curve would tell us what the distance traveled is. This is because distance is equal to velocity times time. So in order to solve for the approximate area underneath a curve, first we have to create a partition of equally spaced rectangles underneath the curve. These partitions can be demonstrated by the equation delta x is equal to b minus a divided by n. B and a are the beginning and ending points of the area we want to find, and n is the number of rectangles that we want to make underneath the curve. Second step is to actually draw the rectangles, and there are three ways you can do this. You can use the left endpoint, the midpoint, or the right endpoint. What this means is that in the delta x of your rectangle, you can use the point at the very left to draw that rectangle, or you can use the point at the very right. So this is how to use left, right, middle, and right endpoints for the rectangle partition. So in this case, we're all going same curve, f of x, from A to B on each one of these. Starting with the left endpoint, you can see that if you try making rectangles in each partition using the left endpoint, meaning the one at the very left, you would get rectangles that go like this. And this is how you would determine the area. As you can see, this is an underestimate because you're not using areas that are underneath the curve. If you go to the middle endpoint, you will find that if you use the very exact middle of your partition and you make a rectangle around it, this is going to be your approximation of the area. This, compared to the left endpoint, is more ambiguous. You have some area that you're not using inside the curve, but there are other areas outside the curve that you are using. For the right endpoint, it's very similar to the left, except in this case it will be an overestimate of your area. As you can see, there are many sections that are outside the curve's domain. So the third step would be to find the area of each rectangle. This means that you can use f of x at any point given times the width delta x that we have determined previously. After that, the fourth step is to find the area of all the rectangles and add it up. Hence, this equation, the total area is equal to the summation of all of the areas found previously. N represents the number of rectangles that you've used in your subinterval. So we're going to do an example now. Our equation for our curve is going to be f of x is equal to 20x minus x squared. And we're trying to find the area underneath this curve in the interval 0 to 20. As you can see here, we have three different notations: L5, M5, and R5. This simply means that there's going to be 5 rectangles that we're going to partition this curve. And the L5 means that you're going to use the left endpoint, the M is the midpoint, and the R is the right endpoint. Now try this on your own. Pause the video and we'll go over the solutions afterwards. So first, for L5, we're going to partition this curve into 5 different rectangles, all with delta x being 4, because 20 divided by 5 equals 4. So now to find the area of each of these rectangles, we have to do delta x times the height of each rectangle. The first one is 0 because we're starting from the left endpoint. But then to find the individual heights, we have to plug in the value 4, 8, 12, 16 into our initial equation. F of x equals 20x minus x squared. Yep. Okay, so as you can see here, we have put all of the values for every single f of x value. 4 over here, 8 over here, and so on and so forth. Afterwards, we add them up, and then we multiply them by 4 because 4 is delta x. Our total is 280. The same is done for the rest. For M5, you use the midpoint at each of these values. So f of 2, f of 6, and so on and so forth. You get the total and you multiply it by 4 again because delta x is still 4. For R5, you do the same as L5 because this 20x minus x squared is symmetrical, right down the middle. So it doesn't really matter if you do the left endpoint or a right endpoint because, as you can see, there is one value that was never used, same as over here. So now we're going to discuss the definite integral and how it relates to what we've learned before about the approximate area. As you may remember, this is the equation that shows the different partitions in a limit in an interval from A to B. If you take a look, if we do the limit of n as it approaches infinity, you'll see that all of these small rectangles that we make will get smaller each time, therefore giving you the exact area. This can also be translated to the definite integral from A to B of f of x dx. So the definite integral will determine algebraically the area underneath the curve from A to B in that interval. So this formula, the integral, gives you the net area from A to B underneath the curve. If you look at this example, you'll see the definite integral from A to B. The issue here is that one of these values, one of these areas is positive and the other area is negative. When this happens, your definite integral is going to equal area 1 minus area 2. A1 is positive because it is above the x-axis, and A2 is negative because it is below the x-axis. So first example is going to be taking the integral from -2 to 2 of the absolute value of x. As you can see here, this is the graph of absolute value of x. And this is the area that we're trying to find. This, if you can see, is 2 times 2. Because if you plug negative 2 into this equation, you're going to get 2. So this is 2, this is 2, this is 2, and this is 2. Therefore, the definite integral of f of x from -2 to 2 is equal to 4. 2 times 2 is equal to 4 divided by 2. This gives you 2. And 2 times 2 divided by 2 is equal to 2. So this is another example. Please pause the video and try and do this by yourself. As you may recall, we determined that a1 minus a2 is going to equal the definite integral of 1 minus x divided by 2 of from -1 to 3. So a1 is going to be the area above the x-axis, and a2 is going to be the area below the x-axis. To determine a1, we can say that this is 3 times 1.5, 3 times 1.5 divided by 2 because it is a triangle, which gives us 2.25. For a2, we can say that it is equal to 1 for the x-axis times -0.5 divided by 2, which equals 0.25. This is negative. As you may recall, we have already accounted for the negative in the previous a1 minus a2, because we know that a2 is going to be negative. So in this case, we can just say that a2 is positive. To find our total area, we can say a1 minus a2 is going to equal to 2, because 2.25 minus 0.25 is equal to 2. These are the properties that you need to know for definite integrals. The first is this, and it can be proven by this section here. If this were a to b, you would have a positive number. But then, if you change a and b, the value is the same, except now it is negative. Therefore, for one to equal the other, a negative sign has to be placed. Now, for the second one, if you're going from a to a, let's say a is here, there is literally no area underneath the curve from a to a, because there is no displacement on the x-axis. And now, when f of x is constant, as shown here, what you find is that if you're going from a to b, this area is going to equal c times a minus b, because c is constant. Properties 4 and 5 are just algebraic rules. The sixth and final property can be explained by a simple graph down here, where a, c, and b are points in the x-axis, and c is more than a but less than b. So when you have the integral of f of x, the line, the curve, from a to c, and then you have that another integral with the same curve from c to b, you're just encompassing one large area with the interval a through b. Therefore, when you add these two, you get the integral from a to b of f of x dx. Now we're going to do another example. As you can see here, we have an integral, and then we have a given f of x from 2 to 4 is equal to 7. So let's break this down. First, we can say, since property 4 tells us that we can break this integral apart, we can say f of x dx, and then minus the same limits of integration for 2 dx. And now if we break this down further, we can say we know that f of x from 2 to 4 is equal to 7. So we've got that part figured out, minus. And now we got to use property 3 to determine what the integral of 2 is from 2 to 4. So therefore, this is equal to 3.
Are you pulling up right here? Is that what's going on?